Let's talk about the normal distribution. What is it? How can we use it? What can we use it for? Let's find out. And we're going to start by looking at an example. And what I'm actually going to do here is I'm going to show these on the screen using sheets. And we're going to take a look at a histogram of adult men's heights. And we're going to see what happens as our sample size increases. So we're going to kind of take a look and then we'll sketch the curve roughly on our note here. So first of all, we're going to look at relative frequency versus height for heights of different men, looking at a random sample of 100 men. So I'm going to switch the screen here, and using sheets and a data set with several hundred heights, let's take a look at what a random distribution of heights for men look like with a sample of 100 men. So all I've done here so far is taken my data set of the heights of men, and I have, let's just confirm here really quick, over 1,000 entries, so about 1,250 data points for the heights of men. And I've looked at the first 100 data sets, and then in Sheets, I just selected those. I'll actually show you really quick so we can quickly review how to make a histogram in Sheets as well. So I'm going to select my first 100 values. So I started at cell 2, so I'm going to end at cell 102. Actually, cell 101. All right, and we are going to go to Insert, Chart, and it automatically chose a histogram, and that's what I want, so that looks good. And so I have a distribution of data. It's in groups, so basically I'm seeing how many data points are between 160 and 162, between 162 and 164, and so on. And we see the shape of our graph, and it's, remember we did talk about the shapes of our distributions before, and we see that it's kind of symmetrical, but not really. There's a few more data points here on the left. Maybe it's like bimodal. Maybe it's a little bit right skew because I got a bit of a tail off here to the right. And so this is a distribution. Let's see what happens when we add some more data points. So I'm going to select more than 100. Maybe we'll go to 250 and see how our histogram changes. So I'm going to pause and go ahead and do that for a moment. We're looking at the same set of data, and I've now selected the first 250 data points. So we're still dealing with the same data set, but now that I have more points, we can take a look and see that our distribution has changed a little bit. So I still kind of have the general shape where there seems to be a bit of a tail off to the right, so it's still a little bit right skewed. I definitely have more data points in the middle now, and it looks a little bit more symmetrical. And we can see our range has extended more too. So now I have a few more values at the lower end where my bottom end here bottomed out at 160, now down to the 157 to 159 range of values. Let's try this again and increase. Let's go to 500 data points. So I'm going to stop and resize and do that as well while we're paused here for a moment. Now we are looking at 500 data points. What do we notice about our graph? Definitely looking a lot more symmetrical now. So I can kind of draw that line of symmetry. We have a bit of a tail off to the left and to the right. And so that's looking pretty good. A little more tidy. And this is kind of what we expect for large data sets of random value, that we would have a normal distribution. We'll talk about those characteristics specifically in a moment. Finally, let's take a look at all of our data. So I'm going to select the entire data set, and let's see how that histogram compares as well. So I'm just going to put this down here so we can compare them all directly. And I'll do that final histogram and we'll come back and take a look at it. And this here is our final distribution, probability distribution graph for our entire 1,250 data points. And what do we see? It looks very symmetrical. I see my cluster of data in the middle trailing off to the left and to the right. So it would not be fair to call this left or right skew. We would kind of just call this symmetrical. It's unimodal. We don't have more than one bump anywhere. And so this is an example of a normal distribution. Let's take a moment now and move on and discuss what does that actually mean? What are the features that make this a normal distribution? And I obviously did not copy those down into my note, but you are welcome to go ahead and do so before moving on with the video. So what makes something a normal distribution? So we've collected our data. We've looked at it in terms of how relative frequency. So how many items are in each category? And let's talk about the shape. So our key characteristics are that it is bell-shaped. And so we've observed that already, but let's sketch it and reaffirm that it looks something like this. So there is our bell. There's my awesome bell. So we can see that bell-shaped and has a single peak at the exact center of the distribution. This is where the mean, the median, and the mode are. It is symmetrical. Half the area under the curve is above the mean and half is below. And so we can draw that center dividing line down the middle. Mean. So symmetrical is one of our key features. It is asymptotic. So think back to your other grade 12 math courses. I can't remember if we touched on it in grade 11 or not. But either way, you should have heard the word asymptote before. An asymptote is that line on the graph that my curve approaches and gets closer and closer to, but never touches. And in this case, that applies to the fact that the curve gets closer and closer to the x-axis, but never actually touches it. The area under the curve represents the probability, and we've touched on that already in our previous discussion of z-scores, using them to find probability with our Brooks-Shields practice problem. And the shape of the distribution is characterized by the mean and the standard deviation. Recall, lower standard deviation means more clustered, therefore the shape is narrower. So if our standard deviation is lower, so think about our previous example about test scores. So if all the test scores are really close together, like for, I don't remember the name in the question, but if somebody scores really consistently, like 68, 69, 70, 71, 68, 72, they're really close, we're going to have a very narrow range, low standard deviation. And larger standard deviation means more dispersed and thus wider. So our other person who had the same average for their test scores, but they scored like 50 and 54, but then also like 85 and 84, and so they were a wider spread, their curve would look something more like that. So the values are more spread out. So lower standard deviation means more clustered, shape is narrower. Larger standard deviation means more dispersed and thus wider. In order to further our understanding, let's take a look at another example as well. So we're going to have a relative frequency. Oops, that's not how you spell relative. Relative frequency of our data. And we're going to have marks on the bottom in percent. And we're going to compare a couple different classes. So, oh, and let's label our marks along the bottom. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100%. I'm not going to fill out all those numbers. 20, 30, 40, 50. Running out of room here. This is the beauty of working with technology sometimes. 60, 70, 80, 90, 100. We can infer the values that aren't shown directly. So let's say we have a weak class with an average mark of around 60%. And so our mean is going to be here. And we have students of wildly varied abilities in this class. And so our distribution maybe is going to look something like this. And so red represents our weak class. Weak class, varied ability. So this is our legend. We use red to represent them. Let's say next we have a stronger class. And with more consistent ability. If we have more consistency, that means our standard deviation is going to be lower, which means the spread or the width of our graph is also going to be lower. So let's say that the average in this class is 80. So I'll draw my mean at 80, and we'll draw our curve, and it's going to be maybe not that narrow. It's going to be narrower though. And one thing to remember is that the area under the graph represents probability. And what is the probability if I add up all the cases or outcomes I'm looking at? It's going to be 100%. 100% of our data points, 100% of our students are represented here. And so basically it's like, well, if the graph is narrower, why is it taller? It's because it needs to have the same area. So if I needed this much space to represent 100% of my class here, I'm just like kind of taking and reshaping. You can imagine even like I have a ball of clay. I spread it into my first pile. Now I'm reshaping it into a taller pile, a taller mountain. It needs to be, but it has to be narrower. It needs to be taller in order to take up the same area, or with the clay example, the volume. All right, and finally, let's say we have a gifted class. Oops, let's make sure we've labeled things properly. And our final example, we're going to have a gifted class. So strong academic ability, and let's say they're very consistent. They all, I forget what the actual criteria is to be officially gifted according to Thames Valley, but basically very, very strong academic skills. Let's say, for the sake of argument here, that the average in our gifted class is 90%. And it's even more consistent than our stronger class. And so our peak is going to be even narrower. So high average and low standard deviation. So that's going to look something like this. So just to get a feel for how does the value of our mean affect our standard deviation, or sorry, affect our normal curve, it moves it left and right. And then the standard deviation, or the value of consistency in the class, how consistent are the values, is going to determine the width of our graph. But overall, the shape is going to be the same. Still going to have those common characteristics of being bell-shaped, of being symmetrical, and of being asymptotic, that it approaches the x-axis but never actually touches it. All right, now that we have some idea of what the normal distribution is, let's learn a little bit more about some of its other characteristics. Next, we're going to talk about the 68, 95, and 99.7 rule, which you may have seen mentioned in our course calendar previously as well. Let's try that again. And let's just talk through this. So we will notice that for any normal distribution x, approximately 68% of the data values of x will lie within the range of mu minus sigma and mu plus sigma. And you're like, well, what does that mean? What that means is that if we start at our mean in the middle, and we go one standard deviation to the right and one standard deviation to the left, that this chunk of my data here includes 68% of all the data points that I'm looking at. And I'm going to erase this to keep it clean. I'll just make the marks as we talk, and then you can label this however you want in your notes as you follow along. We'll also note that approximately 95% of the data values of x will lie within the range of mu minus 2 sigma and mu plus 2 sigma. So what that means, once again, is that if we start at our mean, and I go 2 standard deviations to the right and 2 standard deviations to the left, that this chunk of my curve right here, so this shaded in area, will cover 95% of my data values. And so what that basically means, remember we said earlier, or in a previous video, that the area under the curve represents the probability. And so what that means is that this has an area of 0.95 because the total area under the curve is 1. All right, and finally, the 99.7 rule says that approximately 99.7% of the data values of x, so almost all of them, will lie within the range mu minus 3 sigma and mu plus 3 sigma. So once again, if I start at my median, if I start at my mean and I go 1, 2, 3 standard deviations to the right, And we can see that here. So 1, 2, 3, and 3 standard deviations to the left. 1, 2, 3. So we're finding this area right here. Of course, that includes the whole thing. The area under the curve here will have a value of 0.997, or in other words, 99.7% of my data is represented or is contained within that area. So within 3 standard deviations of my mean in either direction. Now that we have a feel for what the normal distribution looks like and its characteristics, let's see if we can apply it to some problems and practice understanding what the shapes mean and how to sketch them and stuff. So we're going to start by seeing how different standard deviations affect our curve. So you can go ahead and if you're watching this in class, it's up to your teacher to pause. If you're watching it individually, you can do this on your own. But when we get to these questions, I would like you to pause and try to work through them on your own for a couple minutes, either with your group or individually, and then you can proceed and see how we're going to do it all together. So let's start by reading the question first. The length of people's careers at 3 different manufacturing plants are normally distributed with a mean of 20 years of service. Camden plant has a standard deviation of 3.1 years. Dunkirk plant has a standard deviation of 3.9 years, and the Elmira plant has a standard deviation of 5 years. Sketch the 3 normal curves on the same axis. So I'd like you to pause and try that on your own first. Then when you're ready, continue, and we'll do it together. The first thing I decided to do was start by labeling my axes. And so on the left, I have relative frequency, so on my y-axis, and on my x-axis, I have the years of service. And we know from our characteristics up here that the mean is in the middle. So half the area under the curve is above the mean and half of it is below it. So I'm going to start by indicating where my mean is, and it says in the question that my mean is 20 years of service. So let's sketch our curve with that in the middle. Actually, let's label those numbers before we do that. 20, 10, 30, 40. And we're just sketching this freehand, so it doesn't have to be perfect, as long as we get a feel for what this looks like overall. And actually, before we sketch any curves, we should discuss and see what the difference is. So we're going to have 3 different lines. We're going to have Camden plant, which has a standard deviation of 3.1 years. We're going to have Dunkirk plant, which has a standard deviation of 3.9 years. And we're going to have the Elmira plant that has a standard deviation of 5 years. Recall from our previous discussions, we've already gone over this a little bit, but we saw that the higher the standard deviation, the wider our curve is going to be. So lower standard deviation, narrower curve. But also remember that the area under the curve has to remain the same. So as we have a narrower standard deviation, as we take our clay, I like that idea, and push it smaller together, the peak is going to get higher in the middle. So let's take a look at what that's going to look like. Let's also remember what we talked about before, that if we're going like 1 standard deviation to the left and to the right, it's going to be this part of our curve. And so we'll try to kind of sketch accordingly that as we sketch our curve, this top portion is matching up with what we said for standard deviations. So we just said we're going to have a standard deviation of 3.1 years for the Camden plant. 15. Make this a little more granular. And so we're going to be somewhere around here. So 3.1. So 1 standard deviation is going to be about here and here. And let's sketch our curve. And I'm not completely satisfied with that. We'll make it a little bit higher. All right, something like that. There's our Camden plant. Next, let's do our Dunkirk plant. So it's going to be a little bit taller. And our standard deviation, actually it's going to be shorter, sorry, because we're going to be spreading out as our standard deviation increases. So I'm actually going to redo my Camden plant. I'm not entirely happy with that. So something like that. Next, let's do our Dunkirk plant. So we're going to have a standard deviation of 3.9 years. So we're going to go out a little bit further for this part of the curve. And we're going to be spread out more. So we're going to be, let's take a look at something like that. And try to get that good bell shape. Our curve is going to be lower. So it's going to be something like this. Let's make that a little broader still. I'm just not satisfied with that. So we're coming in. All right, and then our Almiro plant has a standard deviation of 5 years. So we're going to go out even further, and once again, it's going to be a wider spread. It's going to be a bit shorter. And our 5-year points are going to be like here. So we're going to have something like that. So how does standard deviation affect our normal curve? It's going to make it lower and more spread out. So we're still going to have that bell shape, and I maybe have exaggerated a little bit too much here. So I'm going to redraw my my purple one for the last plant. But even if the effect is exaggerated, we get the idea of the trends and how changing the standard deviation affects the shape of my normal curve. We can also think about this briefly as we can think of our normal distribution as being like a function. And so what we're doing here is we're applying a horizontal and a vertical stretch and compression. So basically, for example, if we doubled the value of our standard deviation, this is the equivalent to a stretch of a factor of 2 in the horizontal direction, about the line x equals our mean, and a stretch of factor of 0.5 in the vertical direction. So and if you want to relate this to what we might already know in terms of working with functions, we basically have a vertical and a horizontal stretch happening here. And when we talk about changing our mean value, we've kind of already talked about this, and we'll get there in a example question in a moment. But as we change the mean, what that's going to do is introduce a horizontal translation that's going to not change the shape of our graph, but move it to the left and to the right. And let's take a look at that now as we talk about different means. So in our example question here, the weight of 3 different cereals all have a standard deviation of 1.69 grams. So standard deviation is 1.69 grams. So same standard deviation, same scaling factor, same shape. Sugar Yummies has a mean of, Sugar Yummies has a mean of 238 grams. Alphabet Gems has a mean of 301 grams. And Weight Droppers has a mean of 321 grams. Sketch the 3 normal curves on the same axis. Well, anytime we're doing graphing, we want to have labeled axes. So let's have our relative frequency here. Along the x-axis, we are going to have the weight of the cereal. So weight, and that's measured in grams. And let's see what kind of data values we're dealing with. Our averages are going to be in the 300 range, and so that's going to be kind of the midpoint of our graph, and then we'll extend and fill in the rest of the numbers. So once again, I do recommend pausing and trying this on your own or with your group for a couple minutes, and then when you feel ready, you can continue with the video, and we'll work through it together. All right, one thing I do notice here is that my standard deviation is quite small. And we've discussed already that small standard deviation means consistent data, means that my curves are going to be quite narrow. And we also notice that the thing that's going to change here in between my different lines is the fact that they have different means. So standard deviation is the same, means are different. So let's go ahead and make our sketches. So let's start with the Sugar Yummies. They're going to have a mean value of 283. So 50, 25, 75, 83 is going to be somewhere around here. And once again, we're just sketching by hand, so it doesn't have to be perfect. And let's make our curve. We said we wanted it to be quite narrow, so it's going to be something like this. All right, that's not perfect. I want to redo that again. All right, so narrow because it has a small standard deviation, and it is centered. It has the bell shape still, and it is centered around our mean of 283. Next up, let's have our alphabet gems. Has a mean of 301, so let's make our mean right around 301. And the shape should be the same. And I could copy and paste the shape, but then the colors won't match. So I'm going to redraw it to the best of my ability. Same height, because it's going to have the same width and the same area underneath. So not perfect, but okay. And finally, weight droppers has a mean of 321. So 350, 325, that's a good enough approximation. So once again, we're just introducing a horizontal shift, but the shape should be the same. And so we can actually make a little note about that. I guess we could have done that on the previous slide as well, but just like I always say, your notes are your notes, so you don't have to copy everything I write. You can summarize, you can add things that I missed, whatever else. So if you want to go back and add that, that's great. Otherwise, we're going to point out now that when we have different means, shape stays the same, because the only thing that's different is the mean. The standard deviation is the same. So we're going to have the same shape, but we're going to have horizontal translation. So we're just moving that shape to the left and to the right. Higher means obviously mean we're going to move to the right. Lower means mean we're going to move to the left. Next up, we're going to try combining. So what happens if the standard deviation and the mean is different? Once again, I do recommend pausing and trying this on your own in a moment, and then coming back and discussing it together. So the question tells us that the mean height of adult males is 5'10", with a standard deviation of 4 inches, and the mean height of adult women is 5'5", with a standard deviation of 3 inches. So let's just describe what we're going to see here for a moment. For the males, we're going to have a mean of 5'10", and our standard deviation is going to be 4 inches. And then for the women, 5 foot 5 inches, and standard deviation of 3 inches. So what do we notice about the men? Well, they have a higher average or a higher mean, so they're going to be further to the right, and a greater standard deviation, so they're going to be wider. Whereas when we deal with the women, they're going to be a little bit more to the left, and it's going to be narrower because of a lower standard deviation. So with that in mind, let's go ahead and sketch our curve. I'm going to erase what I just wrote here just to not clutter up my page. But of course, you are welcome to pause and make sure you have that written down before we move on. Working with my graph now, I'm going to label. I'm going to have relative frequency. Along the bottom, we're going to have the height measured in feet and inches. So hopefully you're familiar that the single apostrophe represents feet, and the double apostrophe, or the quotation end quotation mark, represents inches. All right, I'm going to pause for a moment while I fill in my axis, and then we'll continue. All right, let's go ahead and sketch, starting with the men. So we're going to have a average height. So adult males is 5'10", standard deviation of 4 inches. So 5'10" is going to be right around here. Let's sketch our curve. Something like that. And then for the women, mean is 5.5, standard deviation of 3 inches. So 5.5 is going to be a bit below 5.5 feet. So we're going to have our mean right here. Standard deviation is lower. That means our curve is narrower, which means it's going to be higher. So that's going to look something like this. And hopefully you got the same thing as well. So what do we notice as we go from the curve of the men? We notice that our curve shifted to the left. So horizontal translation to the left because of the lower mean, and our curve got narrower because of the lower standard deviation, and then taller because it still has to have the same area under the curve. Another feature of the normal distribution that we should talk about a little bit more is interpreting and understanding the area under the curve. So we've said that in general, the entire area represents 100%, all the data that we are collecting. But what happens when we look at different chunks? So interpreting areas, the area under the normal distribution between two x values represents the probability that a randomly selected datum will be between those two x values. So we're finding basically the difference between here and here. And in order to do that, what we can basically do is thinking, so what's the probability of a data point being between A and B? Well, the probability of a probability being less than B is going to be this area here. The probability of being under less than A is going to be here, and we're going to subtract those two values from each other. And how do we find the probability? How do we find the area under the curve? That's when I use my Z table or my Z-score table that we saw in our previous video. Let's summarize that by saying that the probability that our x value is between A and B is equal to the probability that x is less than B minus the probability that x is less than A, and I believe we'll try working through that with an example problem in a moment. Looking at the second half of our page here, we are asked, so we're looking at our curve here, it's very similar to the one we just made. So we have the frequency and the normal distribution for the height of women versus the height of men. Notice that the men is shifted to the right because it has a higher mean, and it is wider and shorter because it has a higher standard deviation as well. The question here is focusing on the distribution of women's heights though, and it asks, what does the shaded area in the left diagram represent? If you know, please go ahead and share. Otherwise, we'll explain this as well. And so we'll notice, we know that the area under the curve represents probability, and we're comparing between two different values here. We're looking at a height of 65 inches and a height of 60 inches. And so if area represents probability, that's our x value, and we're looking between 2 points, basically this area is going to represent the probability that a woman's height is between 60 and 65 inches. So the probability that a woman's height is between 60 and 65 inches. We are also asked to shade in the region that represents the probability that a randomly selected, so I should actually add that here, that a randomly selected. So basically the second question is the same type of question, we're just working in the other direction. Shade in the area that represents the probability that a randomly selected male will have a height between 70 and 80 inches. So we're going to look at the area under our men curve. We're going to be looking from 70 to 80 inches. Let's fill that in. So that's what that shaded area represents. The probability that a randomly selected male will have a height between 70 and 80 inches. For our next example, we are talking about nickels. We are told that the weight of nickels is normally distributed with a mean of 5 grams. So let's highlight our important information as we go. A mean of 5 grams and a standard deviation of 0.1 grams. We are asked to draw a sketch of the distribution and label the x-axis with the mean and multiples of the standard deviation away from the mean. And we've kind of done this before once again with our Brooks-Shields question, so this is not brand new. Once again, I would encourage you to pause and try this on your own or with your group, and then continue when you are ready. We're going to have our frequency. On the bottom, we are dealing with weight or mass measured in grams. And we're dealing with a mean of 5 grams. So draw a sketch of the distribution, label the x-axis with the mean and multiples of the standard deviation away from the mean. So let's start with our mean, 5. Our standard deviation is 0.1. So let's have 5.1, 5.2, 5.3, and 4.9, 4.8, 4.7. Let's sketch. Once again, we know one standard deviation should be kind of the top, like, third of our curve. So something like this. All right, once again, not perfect. It's okay. Curve sketching takes practice. All right, that looks pretty good to me. Oh, and we were supposed to label in terms of standard deviations as well. So I'll kind of add that here. We did this previously as a separate axis, but I'll label my Z values here. So Z is 1. How many standard deviations have I moved to the right now? 1, and 2, and 3, and -1, -2, and -3. And of course, we can match that shape up with what we saw before. 68% of the value is within the first standard deviation, 95 within 2 standard deviations to the left and right, almost all the data within 3 standard deviations to the left or to the right. And so I use that to inform my curve sketching as well, that within 3 standard deviations, I have basically all of my data, 95% within 2 standard deviations, 68 within 1 standard deviation, and so on. And once again, it's not perfect. We're just curve sketching by hand, but it gives us some direction. All right, so we finished A. Let's take a look at B. What is the range of weights that 95% of the nickels fall into? Well, we just saw that. Let's go back and reconfirm. We know that 95% of the data fits within 2 standard deviations to the left and to the right. And so let's show that on our graph. 2 standard deviations to the left and to the right. So here and here. And we can quickly say that, therefore, 95% of the nickels weigh between 4.8 and 5.2 grams. And so that's helpful because what we know, because of what we've learned about normal distributions and their characteristics, we can quickly answer a question like this using our 68%, 95%, and 99.7% rule. Let's also answer an example question about babies and their weights. And so it's kind of important, like, basically we use normal distributions when we're dealing with large populations of things. So like you're producing nickels and you have to actually measure and make sure that they have a consistent weight and a low standard deviation and stuff in manufacturing. And same with babies. We often use normal distributions to talk about or use it to describe or determine the health of babies. So sometimes when somebody has a kid, they'll talk about, oh, they're in the 99th percentile for their weight or their height or their intelligence or whatever. And that's referring to what portion of the normal curve they're under. And when we talk more about percentiles and interquartile ranges and stuff in the next couple days, that'll make a little more sense as well. Anyway, let's dive into this question. Let's see what's being asked. Let's try it on our own, and then let's work through it together. The weights of babies of a given age and gender are approximately normally distributed. Boys at 6 months have an average weight of 17.25 pounds. Let's highlight our important information as we go. Average weight of 7.25 pounds and a standard deviation of 2 pounds. At 12 months, the average is, so 6 months was important. And at 12 months, the average is 22.5 pounds and a standard deviation of 2.2 pounds. All right, I paused the recording there for a moment, so I don't remember exactly where we were, but basically we have 2 different distributions for boys at 6 months and boys at 12 months. We're going to draw the sketch, and we're going to start by labeling our graph. Once again, I recommend pausing and working through this on your own for a minute to try, or with your group, and then taking a look at it together. So we're going to draw the sketch. We're going to have the relative frequency off to the side on our y-axis. On our x-axis, we're looking at weight, measured in pounds. And we're focusing around 17 to 22 pounds. So I'm just going to choose like 20. And then we can go up 21, 22, 23. And 19, 18, 17, 16. 15, 14, and then we'll draw a little zigzag to jump. So we're starting at 0 here and then jumping up. All right, let's sketch our curve. So in the first case, 6 months, average weight of 17.25. So that's going to be around here. Standard deviation of 2 pounds. So, you know, 65% of my data is going to be, 68% of my data is going to be included in there. So that's going to be kind of this part right here. Let's draw our sketch. All right, so that's for 6 months. I'm just kind of having a legend here to label my curves. And then at 12 months, we'll use red. And at 12 months, the average is 22.5. Should have included a few more values here, so I'll just add those in right away. 24, 25, 26. And once again, we know that 68% of our data is within 1 standard deviation. And our standard deviation is 2.2 pounds. So 22.5, 23.5, 24.5. And 1, 2, around there. And our standard deviation is very similar. It's slightly larger, so our data is going to be spread out a little bit more, but not too much more. So the height is going to be slightly lower, but not a lot. So something like this. And something like this. I don't love that. There we go. That's okay. All right, we've sketched our 2 curves. They're labeled. Let's take a look at our next question. Approximately what percentage of 12-month-old boys have a weight of more than 24.7 pounds? All right, let's take a look. So we're looking at our 12-month-old boys. So we're looking under our red curve. And have a weight of more than 24.7 pounds. 24.7 is going to be right around here. And I'm trying to figure out this area right here. You'll notice that when we talked about using the Z tables, we were just looking at the values to the left. So what we're going to do is we're going to kind of use like our indirect method like we've done before for other questions. I'm going to find this area here and subtract that from 1. So let's go ahead and do that. It does say approximate, and so I'm going to kind of approximate here. We've been working with our standard deviations, so let's think, how many standard deviations am I away from the mean? So I was at 22.5. If I go to 23.5, that's 1 standard deviation. So let's see, we were at our mean here, so that was our mu. We're at 1 sigma. And then 24.5, we're looking at 24.7, so it's not quite the same, but it's pretty close. So we're 2 sigmas away. And what do I know about being 2 sigmas away from the mean? Well, I know that this area right here is going to be 95% of my data. So that means that this chunk here and this chunk here are each going to represent the other 5% of my data. And so I actually don't even need to do the calculation here. I can just stop and think about it. So the whole curve is 95%, or sorry, the whole curve is 100%. This is 95. Whoops. This is 95. This is half of the remaining 5%, so 2.5. So I've used up 97.5%, which means my remaining piece here needs to be 2.5%. Or even automatically, I know right away that my two green curves here represent 5%, one half and the other half because it's symmetric. So it's just going to be half of 5%. It's just going to be 2.5%. So whichever way we decide to think about it, whether we calculate directly, so 1 minus 95% minus half of the remaining 5%, or we just know that it's 5% for my n pieces divided by 2. Either way, we're going to end up with a result of 2.5%. So therefore, approximately 2.5% of 12-month-old boys have a weight of more than 24.7 pounds. And it's not exact. We're using our rule, our 68, 95, 99.7 rule, which is an approximation. We're also observing that the Z score is approximately 2. They're approximately 2 standard deviations away from the mean. Not exact. We could find an actual Z score and calculate a little more specifically and stuff, but the question just said approximately. We found approximately. That's good enough. For question C, approximately what percent of 6-month-old boys have a weight between 13.25 and 21.25 pounds? And let's take a look, see if we can figure this out quickly based on standard deviation, or if we need to actually calculate a Z score. So we're looking at the 6-month-old boys, so the blue curve on the left, have a weight between 13.25 pounds, so that's going to be around here, and 21.25 pounds, which is going to be actually up here. So let's actually extend our blue curve a little bit here. Remember, it does extend forever. It never actually reaches the x-axis, so it can extend to whatever values we need. And maybe I should have spaced my graph out a little bit more to have a little more, show a little more of the curve. So if you're doing this in your notes, you may wish to extend or correct that right away. This is also my first time doing this question, so I did not know to scale it a little bit bigger. All right, and so we're looking at quite the range here, from here to here, and finding the area under our curve. We know for the 6-month-old babies, the standard deviation is 2. So let's count how many standard deviations away we are. So 17 to 19 is 1 standard deviation. 19 to 21 is 2 standard deviations. And we're a little bit beyond 2. So we're at 21. And our value here is 21.25. So we're slightly beyond, but we're pretty close. And then moving to the left, 17, 16, 15. So 1 standard deviation. And we're at 13.25. So 14 and 13 was like here. So yeah, I didn't scale my graph entirely correctly. But we can see that we're basically within 2 sigma in either direction. So 2 standard deviations. What do we know about moving 2 standard deviations to the right and to the left of our mean? We know that that encompasses 95% of my data. So once again, approximately what percent of boys have a weight between those 2 points? Well, those 2 points represent 95% of my data. So approximately 95% of 6-month-old boys have a weight between those 2 values. Once again, it's not exact. Actually, sorry, it is pretty exact because our average weight was 17.25. So we're not at 17. We're already offset by that 0.25 there. So we did go all the way to 21.25 here and all the way to 13.25 here. So that works out nicely. Let's write our conclusion then. Therefore, so we're within 2 standard deviations of either direction, so 95%. Therefore, 95% of 6-month-old boys have a weight. Just going to use some short forms to save some room here, between 13.25 pounds and, and 21.25 pounds. All right, so it turns out the normal distribution and our 68, 95, 99.75 rule are pretty useful and let us answer some pretty interesting application questions pretty easily. Finally, for your practice work, and don't worry about this just because we're using this note. Finally, for your practice work, you can work on that practice sheet that was posted to Classroom. So some of you may have worked on it already. I know some of you had some challenges with that. But now that we've gone through the actual lecture together with me, as opposed to like Miss Brown's version that maybe referenced things that hadn't happened yet in her class and stuff, hopefully it makes a little more sense. Please try that practice work with your group. Check some answers, and then if we still have questions, that's something we can revisit when I'm back in class in person, or we can try to discuss online during your study halls as well.